Hi everyone, my name is Julia Tupper and I am part of the Lee Research Group at UMass Amherst. Today I will be discussing a project that I have been working on for the past 2 years, the tissue engineering of the bone environment using demineralized bovine bone strips. The goal of this project was to produce a freestanding analog from demineralized bovine bone that emulates the complex bone environment, as well as allowing for the control of bone thickness to demonstrate bone loss with age. The image on the left shows the bone remodeling process that accounts for bone loss and rebuilding over time. The balance of bone buildup and breakdown is crucial to maintaining healthy bone. As you can see in this image, osteoblasts build up bone and osteoclasts break bone down. The rank OPG pathway is critical in the bone remodeling process. Rank ligand, a key factor for osteoclast differentiation and activation, binds rank, allowing for bone resorption. Whereas when OPG is expressed, it binds rank ligand, which inhibits osteoclast function. Osteocytes play a crucial role in recognizing sites of bone damage and age and direct osteoblasts and osteoclasts accordingly. The image on the right shows that bone mass levels off with age and then declines. This occurs as bone remodeling becomes dysfunctional and leads towards more absorption over time. This graph from the US Surgeon General in 2004 demonstrates that decreased bone loss and osteoporosis were projected to increase in the years that we are currently living in. These statistics can be confirmed from the recent increase in bone disorders and the projected further increase that will be occurring in the years to come. These daunting statistics demonstrate that there is need for research on the bone environment and the comprised remodeling processes that occur with age. As you can see, cortical bone is quite complex, with its layer by layer lamellar formation. The goal of this rolled bone paper structure is to use the demineralized bovine cortical bone to emulate the lamellar structure with rolling, as well as to address a key limiting factor of many current bone tissue models, which would be to incorporate the study of both cells on the surface of the bone and within the bone for a more accurate representation. This demonstrates the beginning of this process, which starts with demineralization and with the removal of fat and tissue from the bovine bone, followed by a 1-to-1 chloroform methanol treatment. The hydrostatic pressure chamber with 1.2 molar hydrochloric acid is then used to complete the decellularization and demineralization, while still maintaining the important bioactive components of the bone. This figure demonstrates the process of first freezing demineralized bone in OCT, cutting the bone with the cryostat machine into 20 micrometer pieces, and then arranging these pieces into a plastic tray. The pieces are submerged in a 5% PVA or polyvinyl alcohol solution and arranged in a 6x6 manner, and then allowed to dry for 2 to 3 days. The dried PVA sheet is then extracted and cut into the desired shape using a CE6000 plot cutter machine. Once the pieces are cut, they can be weaved. Next up is the process of cell seeding, rolling, and culturing to produce this freestanding analog that mineralizes. I haven't done much of this semester due to COVID restrictions, but these pictures are from previous semesters and can give you an idea of the process. And in this process, we use primary mouse osteoblasts for the cell seeding. Here's just a schematic of the design used for weaving. A lot of what I did in the process of doing is to refine the efficiency for the strip production process. Cutting all of the pieces at the same time, using this template when placing bone strips in a 5% PVA solution, has greatly increased cutting efficiency, going from about 1 to 1.5 hours to about 7 minutes for this process. A place for improvement in the future would be a technique or a design for a more efficient weaving, because this is still a process that takes a while. Here's a time lapse of cutting an entire 36-piece sheet at once, a process that has greatly improved the efficiency of strip production. And this video is sped up, but in real time it takes about 7 minutes. These graphs demonstrate that using increased numbers of 5-piece strips will increase the thickness and the number of rounds in the freestanding analog. And on the right are some histological images from Youngkook Park, a graduate student in the Lee Lab. The histological images could verify the theoretical rounds and thicknesses based on the number of strips used. For the future, a bone marrow insert and a muscle ring could be incorporated into this model for a more accurate emulation of the bone environment with aging. This model will have an important application for age-related bone disorders, which are currently affecting millions of people, with a great projected increase in the near future. This model will address many of the current limitations displayed by current in vitro bone tissue engineered models, as well as provide crucial information regarding the complex bone environment, along with implications for understanding bone diseases with age and possible cures, therapies, and/or treatments. Lastly, I would like to thank my PI, Professor Lee, as well as Eugene Jiang and Youngkook Park, who have helped me greatly in this project. I would also like to thank the rest of the Lee Lab for their continued support and hard work. Thank you, everyone.